China just dropped something wild into the AI race. And honestly, it feels like one of those moments where the entire industry shifts overnight. We're all used to hearing about quantum computers locked away in giant labs, hooked up to cooling systems the size of a small house. That kind of tech always feels distant. But this time, the story lands right in the middle of real-world computing, because a Chinese research team just built a quantum photonic chip that actually works inside normal data centers. And yeah, the numbers they're claiming almost sound fake at first. Something like a 1,000-fold speed boost over Nvidia GPUs for certain AI workloads. Not in 5 years. Not planned. They say it's already deployed across aerospace, biomedicine, finance, all the heavy computation sectors. So let's walk through this carefully because, to be honest, there's a lot going on. The chip comes from ChipX. That stands for Chip Hub for Integrated Photonics Explorer. They teamed up with Turing Quantum, and together they announced what they're calling the world's first scalable, industrial-grade optical quantum chip. And honestly, the hardware size is the part that hits the hardest. This isn't some refrigerator-sized monster. It's a 6-inch, thin-film lithium niobate wafer with over 1,000 optical components etched into a single slice of silicon. That's the whole point of photonic integration. Everything shrinks dramatically while still tapping into quantum classical hybrid architectures. Now, what makes this chip so different is that it uses light as the carrier for qubits in computation, instead of electric signals or matter-based materials. Photons move faster, they lose less energy, and they don't create heat in the same messy way electrons do. You end up with smoother data movement, higher efficiency, and way lower thermal overhead. And right now, data centers are choking on heat and power consumption. Everyone keeps talking about how expensive it is to train large AI models. So, a chip that pushes information using light instead of raw electrical current hits exactly where the pain is. Obviously, the 1,000 times claim is what made headlines. It comes from the South China Morning Post and statements from the developers saying these chips accelerate complex problem solving by a factor of 1,000. And they claim the chip is already deployed inside live data centers. Now, to be clear, it's not 1,000 times faster at everything, far from it, but for tasks that benefit from quantum-style parallelism, super low latency, photon-level routing, and massive optical bandwidth, the speed absolutely can spike past classical hardware. Anyway, the scalability story is where things get even more interesting. One of the biggest problems with quantum systems is how massive and fragile they are. Normally, you need months to assemble and calibrate hardware. ChipX says that systems that usually take 6 months to put together can now be deployed in about 2 weeks thanks to the photonic design. 2 weeks for something operating close to quantum classical territory is honestly insane. And no, this isn't a full universal quantum computer that cracks encryption or does sci-fi teleportation tricks. This is photonic quantum hardware optimized for AI and high-speed data processing, running on hybrid logic. So, the chip works like a programmable photonic accelerator. It processes information by manipulating light's properties, color, timing, phase, distribution, and connects thousands of optical components inside one monolithic architecture. And the monolithic part is what caught the attention of Western researchers. Everything sits on that same 6-inch wafer with no huge external modules. It's integrated into one piece of silicon. The team behind it won the Leading Technology Award at the 2025 World Internet Conference Wuzhen Summit. They went up against more than 400 global entries from 34 countries. Winning that signals that China has jumped ahead in at least one corner of photonic quantum hardware, especially when you look at production. ChipX launched a pilot production line earlier this year that can output around 120,000 wafers annually. Each wafer yields roughly 350 chips. And that's not mass production by semiconductor standards, but for quantum classical photonic chips, that's higher volume than anyone expected China to hit right now. They admit production is still the bottleneck. Thin-film lithium niobate is incredibly delicate, yields are inconsistent, and getting uniform chips across an entire wafer is still difficult. But even with that, they've built a complete closed-loop supply chain. Chip design, fabrication, packaging, testing, and full system-level integration all happening inside the same ecosystem. Meanwhile, in Europe and the US, photonic chips are still mostly at the prototype or small batch stage. Smart Photonics in the Netherlands just upgraded to 4-inch indium phosphide wafers. Psi Quantum in California is working on adapting 300mm silicon photonics for their quantum roadmap. But China built a functioning 6-inch thin-film lithium niobate pilot line. It's a moment where you realize the race quietly shifted. Nvidia isn't sleeping either. They're investing in optical and quantum technologies. The electrical pathway for AI is hitting a wall. Power consumption is through the roof. Companies training large models are spending more on electricity than hardware. So photonics is the direction everyone is sprinting toward right now. What stood out is how quickly these photonic chips can be clustered together. The architecture supports scaling up to 1 million qubits of quantum processing power. These qubits aren't the same as superconducting qubits in deep-cooled quantum computers. But the fact that you can stack these chips like GPU clusters means the whole thing behaves like a massive quantum-inspired processing grid. It's parallelized from top to bottom, photons, pathways, and wafer-level integration. And the chip isn't just about speed. It promises stability and extremely low power consumption too. Since photons don't heat up the way electrons do, you avoid the thermal runaway problems that plague data centers. And because light can carry more information per unit of energy than electrons, you get more bandwidth, better compression routes, and less interference. It's the kind of thing that can speed up model training or data center pipelines. A lot of these claims still need independent verification. The reports made it clear that we don't know every limitation. We don't know long-term failure modes. And we don't know what tasks are behind the 1,000 times faster label. But every major quantum classical hybrid breakthrough starts this way. Early adopters take the lead, and right now China wants to set the pace. China is already using these chips in aerospace, biomedicine, and finance. These industries rely on simulations, molecular modeling, pattern matching, cryptography, algorithmic trading, all kinds of computation-heavy work. Photonic quantum acceleration is perfect for that. And because the chips don't require exotic cooling, companies can drop them into existing racks and cluster environments. The chip uses a new co-packaging method that places electronic and photonic components side by side on the same wafer. That reduces latency, noise, and dramatically boosts bandwidth. Since photons don't have to travel far inside the chip, error rates drop. Lower error rates mean higher throughput. It's the same optimization philosophy we've seen in top-end classical chips, but pushed further because photons behave differently than electrons. China's timing is interesting too. The US, Europe, and a bunch of global research groups are accelerating their photonics programs. Quantum computing is in this stage where no one fully owns the race. Google and IBM are still pushing superconducting qubits. PsiQuantum is going all in on silicon photonics. Europe prefers indium phosphide. China is betting on thin-film lithium niobate, and they already built the factory and delivered the first deployments. So they're not just making a bet, they're executing. The line that caught everyone off guard was this: the first time optical quantum computers can be considered industrial-grade products. That's a mindset shift. They're treating this not as a lab experiment, but as something that belongs in data centers next to GPUs. If that mindset sticks, the next few years could look completely different. Maybe photons start handling the heavy lifting while classical silicon handles everything else. Nvidia GPUs will stay around, but they might not be the only major player in high-end acceleration for much longer, especially as power demands climb. Alright, that's the full breakdown. Drop your thoughts below, subscribe for more deep dive AI coverage, and I'll catch you in the next one.